All right, hello, good morning, and some thoughts now on the sine and cosine functions. Again, our goal with this chapter is to grab all the functions that we've looked at from pre-calc and before and try to figure out if they're differentiable, what is the rule for their derivative, right? What are these speedometer functions sitting behind the functions that we've seen so far? So sine and cosine are next up, and these are the functions that model anything that oscillates or has a periodic behavior. And so this is of utmost importance to engineers, those of us going on into physics, but also studying any natural phenomena. Anything that oscillates or fluctuates can be modeled with sine and cosine to a shocking degree, in my opinion. So we have the base sine curve, just refreshing you on its graph. Remember, if we feed the input in x in radians and not degrees, you might have to shift your mode in your graphing utility. But what it does is it starts at 0 and bounces between 1 and -1 and back to 0 over a span of 2 pi radians, or a full rotation. Again, remembering that this comes from the height as we traverse the unit circle, right? Your height at a given angle of rotation. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Sine is the height. So you're at 0, then 1, then 0, then -1, then back to 0. And so you can see the correlation between these two. So circular, repeated behavior, and then this kind of oscillating behavior as well. So they kind of take on both. And so for sine, right, our goal is to come up with a derivative function, so something that models the slope of its tangent line at every point. So if we take a look at each of these maybe key points and come up with something, we see, well, the slope is positive here. The slope is actually very close to 1. Here, where it turns around, we see the slope is equal to 0. Say approximately 1 here. Here, the slope is actually approximately -1. Again, you can't really necessarily tell this from the graph, but if you were to zoom in and adjust your window, you'd see this is the case. Down here, see again, the slope is 0. And then back over here, by the fact that this is a symmetric repeating curve, the slope should be approximately 1 as we get closer to 2 pi. All right, so what are we seeing? That the slope here goes from 1 to 0 to -1 to 0 to 1, the slope of the tangent line for sine. Okay, and so if we were to graph this function, which started at, let me do this in blue, that took on this value. So again, y equals f prime of x, its output is the slope. So the slope is 1, the slope is 0, the slope is around -1, the slope is 0, and the slope is 1. Gee, what does this function look like? Well, this looks exactly like y equals cosine of x. So in fact, this is how these two are related. That sine and cosine are related by their instantaneous rate of change. And for y equals sine, y prime is cosine. Okay, now this does not constitute a proof, but it gives us this intuitive understanding of how they're connected, okay? Which for our intents and purposes is totally fine. And in the same way, we can take a look at cosine and say, all right, well, you're a periodic function. You repeat yourself over and over, which means that your slopes will be repeated over and over. So it makes a lot of intuitive sense in that way. Okay, so here we're starting with a slope of 0, slope of -1, slope of 0 again, slope of, I should use approximation here, slope of 1, and then again slope is 0. So what does this look like? Well, slope is 0, Slope is -1 here. Slope is 0 here. Slope is 1 here, and then back to 0. So it's doing something like this. Okay, now this looks similar to a sine function, but it's not exactly sine. What it is it's negative sine x. So it's the opposite of sine x. It's been reflected over the x-axis. Okay, so what this tells us is that for f of x equals cos x, f prime is actually negative sine x. Okay, so it's not exactly that, you know, that they are each other's derivatives. Cosine is the derivative of a sine, but the derivative of cosine is negative sine. Okay, and so that's the relationship here, and this is something that you can easily overlook. But to make sure that when you differentiate cosine, that you negate that sine function. So just to kind of fill in our notes here, what can we conclude about sine and cosine? The derivative of sine is cos. The derivative of cos is negative sine. All right, and so for those of you coming through with me on all these lectures, here's exercise 3 in this text. It's a bit of a formal exploration as to why the derivative of sine is cosine. Right, I gave you kind of an intuitive idea of why, but using the limit definition, which we are emphasizing here, why is it the case? So we're going to kind of walk through this a bit in line with the exercise, but also I'm going to kind of do my own thing at the same time. So the idea is to unpack this and see how is it that we get from here to cosine. Okay. So the first thing we want to do for part A is recall a helpful identity. Since sine and cosine are so closely related in terms of their shape and phase shift, there's a lot of equations that relate them to each other. And this is one of them, and you probably haven't seen it in a while. But it's the angle sum formula. And why this is helpful is because I have a sum in my difference quotient. All right, so this is telling me that sine of x plus h is equal to sine x sine h plus, oops, I did that wrong, sine x cos h, right, plus cos x sine h. Gearing up for the next part, which is then to represent the top of this difference quotient, which is the limit as h goes to 0 of, well, this sine of x plus h is this part we just found. The whole point of this is to get this into a more workable form, and then we'll subtract the sine x that was already there, all over h. So all we've really done is just replace this sine x plus h with this identity that we got. And then we can simplify this by pulling this term over here and factoring it out. So I'll get the limit as h goes to 0. You'll see sine x cos h minus sine x. I can pull a sine x out of both of those terms, and I'll be left with cos h minus 1 plus cos x sine h. It's getting a little cos x sine h, okay? All over h. So you'll see, maybe this wasn't super clear. For those of us a little rusty with factoring, I give you this. Okay, factor out the sine x, and that's what you're left with. So why that is helpful is because now I can do a little bit with this limit. It's not so intermingled with x and h. Things are a bit more split up. So what we can use is the fact for b. Since h is going to 0 and x is treat it as constant, that means that sine x, cos x are fixed for the moment. Which means you can treat them as scalars in a limit. And if you remember our laws for limits, that means we can pull out that scalar until the very end, right? It's not affecting the limit besides just scaling it. So we can, in a way, think about it like this. So think, all right, if I've just got the top of this fraction, sine x cos h minus 1 plus cos x sine h, this is all over h, but really I can think of this as two terms both having a common denominator of h, right? It's the case that a plus b over c is a over c plus b over c. So this is all I'm using, and I'm going the opposite way on this equal sign. Again, to get it to be a more workable form. And the reason that I do that is because I can split limits over sums. So this tells us that the limit of all this as h goes to 0, sine x cos h minus 1 all over h plus cos x, plus the limit as h goes to 0, cos x sine h all over h. So this is really, f prime of x equals this through this chain of thought. And what I said before was that we can treat sine x and cos x as fixed. So I'm just going to grab this and move to the next slide so we get some more space. Okay. So from here, this means, using that limit law of scalars, that is equal to sine x, I'll pull that out to the left, times the limit as h goes to 0 of cos h minus 1 over h plus cos x times the limit as h goes to 0 of sine h over h. The whole point is to get this to be something a little bit more workable, so hopefully we can figure out what these limits are. Now, through a graphical or table exploration, you can figure out what these are. You can approximate what these are pretty easily. And so what I'll do is pull over this graph here. So you'll see in red is the cos h minus 1 over h limit. I'm just using x as my variable here. Maybe I can put it like that. And sine x over x for my sine h over h limit. And so we want to approach 0 with the input, so we're coming to x equals 0 here. And we know it should be undefined at this point. And since I clicked that, it won't show me that. But it is. Will it not let me see that? It won't. Okay, anyway. So it is undefined here, and we know that because x is 0 and it can't be expressed. But we see what it's approaching. The further I zoom in, we see that this limit is actually approaching 0. And the same thing is the case for this limit up here. The function itself is undefined at x equals 0. See, there it goes. But as I zoom in and we take the limit numerically, it is, unassailably going to 1, right? So what we can say here is that we know this is going to 0 and this is going to 1. And so what does that tell us? Well, that the limit is equal to sine x times 0, which gives us 0, plus cos x times 1, which is cos x, so that just leaves us with cosine of x. And so that is why the derivative of sine is cosine, leaning on the limit definitions instead of just that intuitive bit that I gave before. So hopefully this helps you kind of from a different perspective, especially those of you who are moving on into higher mathematics and into proof-based things, how we kind of come up with these ideas and, again, from our definitions, get to these inescapable conclusions of, how these things are related. So it's, we don't just invent these things. They follow as how we've very clearly set up our definitions and assumptions. So it's very much a science. So yeah, I'll leave it here. Hope you have fun. We'll see you in the class discussion.